Good morning. I am Dr. Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today, I am going to discuss active filters. Actually, before starting of discussion of active filter, let us talk about filters. As name suggests, filter means the something which can filter out something. Or if I will talk in terms of electronics, that means the filter is a device, is a circuit which can filter out some particular range of frequencies. Actually, there can be several frequency in a signal, or we can say that signal have various frequencies. So, we are interested in some particular range of frequency. For example, there is a signal of around there are the signal of 1 megahertz, 2 megahertz, 5 megahertz, and I am interested in the signal of 2 megahertz. Then other signals are useless for me. That means somehow I need to filter out those signals which are out of interest. So, I must concentrate on the signal on which I am interested, and for that purpose, or to filter out that purpose, I need filter. So, filter is an electronic device, filter is an electronic circuit that passes some particular range of frequencies while stops or attenuates other range of frequency. So, depending, actually these circuits are designed with the help of either active components or passive components. So, from here the name active filters and passive filter comes. Generally, if there is sufficient signal strength is there, then we need not to enhance the signal strength, and for that purpose we can use passive filters. So, passive filters are the filters which uses passive components only, like resistor, capacitor and inductor, and they are generally useful for 100 hertz to 300 hertz. And passive, if the signal will pass through passive filter, then signal strength will decrease and they cannot provide any kind of gain, they cannot increase signal strength. While active filters are capable of dealing with very low frequencies and they can provide voltage gain. And passive filter, if we will use passive filter, and with passive filter, if we will use one active device, then that filter will convert into active filter. So, active filters are the devices which uses resistor, capacitor and at least one active device like operational amplifier. But generally inductors are not used in active filters because their size is quite large. So, depending on the type of frequency the filter going to pass, we can categorize filters into 4 parts. This is a categorization of passive filter. However, we can also categorize active filters in these 4 categories depending on the range of frequency which filter is going to pass. So, one is low pass filter, high pass filter, band pass filter and band reject filter or notch filter. So, if you will see, this is what? This is nothing but this is low pass filter, where I am going to use one resistor and one capacitor, and when I will apply some input signal, and for example, its cutoff frequency is Fc, then this signal will this filter will pass all these signals which have frequency less than Fc and stop all other signals which have frequency more than Fc. Graphically, we can represent this filter response like this: constant, almost constant amplitude, then it will decrease. This is practical response. That means it will behave practically like this. Gradually the gain will decrease, and at this cutoff frequency, which is minus 3 dB cutoff frequency, if this gain is in ratio, then it will be 1 upon under root 2 times, and if this gain is specified in dB, then it will be minus 3 dB of maximum at this frequency. And ideal response is shown like this. This is actually ideal response. All signal pass before this frequency, and it will stop all the signals after cutoff frequency, but it will happen ideally. Practically, there is no filter which can behave like this, that it will pass all the frequencies before cutoff frequency, and immediately after cutoff frequency it will stop all the signals which have frequency more than fc. No, practically it is not possible. Practically what happens? Practically it happens that gain decreases slowly with respect to frequency. So at cutoff frequency, practically the gain reduces up to 1 by under root 2 times of maximum gain, and after that gain used to decrease. This is what happens in case of filter. Obviously, we can see that there are two passive components, resistor and capacitor. So this is passive filter. If I will use operational amplifier with this filter will convert into active filter. Later on we will discuss active filters also. This is high pass filter. We have interchanged the position of resistor and capacitor. High pass filters are those which passes the signals which have frequency more than cutoff frequency. So it should be the ideal response of the high pass filter, and practically it will behave like this. At high frequency there is sufficient gain, at cutoff frequency gain will reduces to minus 3 dB, and after that the gain decreases. So at lower frequencies gain will be almost 0, attenuation will be infinite, attenuation will be very high. As frequencies will increase, attenuation will become less and gain will increase. So these type of filters passes high frequency and stops low frequency. That's why this filter has name high pass filter, passes high frequencies. Next is the band pass filter. It passes the band of frequency ideally between these two. Practically it will be like this. So it is clear from its name that band pass filter passes the band of frequencies. Obviously it is this time it is passive filter because there is no active component associated with this circuit. Next is band reject filter. It rejects band of frequencies. For example, in this band it will not pass anything, it will stop. Before this cutoff frequency it will pass the signal, after this frequency it will pass the signals, but between two frequencies it will stop the signals. So this filter has name band reject filter because it is going to reject the frequencies between this band. It will pass before F1, it will pass after F2, but it will stop between F1 and F2. So it is just opposite of band pass filter. Band pass filter passes band of frequencies. Band reject or band stop filter rejects band of frequencies. You can see this diagram. Actually, band reject filter can be designed with the help of low pass and high pass filter, but these two should be connected in parallel. If you want to design band pass filter, then low pass filter and high pass filter should be cascaded together. They should be connected in series. But we need to remember that in this case, the cutoff frequency of low pass filter should be less than the cutoff frequency of high pass filter. otherwise it will become all pass filter. Similarly, here if you are going to connect low pass and high pass filter into the series, if you are cascading these two filters, then in this case the cutoff frequency of low pass filter should be higher than the cutoff frequency of high pass filter. Only then it can become band pass filter, otherwise it will become all pass filter. Now, these are few terms which we need to remember, like minus 3 dB frequency. Minus 3 dB frequency, as we have discussed earlier, minus 3 dB frequency is the frequency at which gain decreases to 1 by under root 2 times if gain is specified in ratio. If gain is given in dB, that times the gain should be decreases to 3 dB. That means, for example, maximum gain is 20 dB. I can write it 20 dB. If it is decreased by minus 3 dB, that means 17 dB. So, whatever frequency we are going to get at 17 dB will be the 3 dB frequency. Very simple. Next is center frequency. Actually, the term center frequency arises from band pass filter and band reject filter. As we have seen earlier, band pass and band reject filter have two frequencies, F1 and F2. Here F0 is also mentioned, which is nothing but center frequency. Similarly, here F1 and F2 are two cutoff frequencies and F0 is the center frequency. So, the center frequency, a term used for band pass and notch filters, is a center frequency that lies between the upper cutoff frequency and lower cutoff frequency. The center frequency is commonly defined and find out with the help of arithmetic mean or geometric mean of lower cutoff frequency and upper cutoff frequency. That means you can find out F0 by F1 plus F2 divided by 2. This is geometric mean, or F1 into F2, it's under root. Both you can use. Now, bandwidth, all of you know, bandwidth means the band of frequencies. How you can get it? You can get it by subtracting lower cutoff frequency from higher cutoff frequency. For example, F2 is 100 kilohertz and F1 is 50 kilohertz, then 100 minus 50 will be the 50, so 50 kilohertz will be the bandwidth. Now, stop band frequency. This is particular frequency at which the attenuation reaches specified value. For example, if I will take this response, this is frequency, this is gain, then here we have sufficient gain, but in this region attenuation is increasing. So, stop band, if we are going in a stop band, then this particular frequency at which attenuation reaches specific value, you can mention that attenuation, and depending on that you will have that stop band frequency. Next is the quality factor. Quality factor Q is equal to F0 upon F2 minus F1, where F0 is the center frequency and F1 and F2 are two cutoff frequencies. Now, let us come to the active filters. After understanding these basic concepts, we can go for the active filters. Active filters with passive filter circuit containing multiple stages, this loss in the signal amplitude called attenuation. This is the disadvantage of passive filter. So, one way of restoring controlling this loss of signal by using amplification through use of active filters, and active filters can use either operational amplifier, transistors or FETs. So, generally we will use active filters, and again active filters are categorized as active low pass filter, active high pass filter, active band pass filter and active band stop filter. So, let us discuss low pass filter. The principle of operation of frequency response is exactly the same for those previously seen low pass passive filter. That means it passes the frequencies less than cutoff frequencies and stops the frequency more than cutoff frequency. We are familiar with this circuit of low pass filter. So, now let us analyze this circuit. How does this circuit will behave when we will apply the signal of some particular frequency. So, just to find out the response of filter, actually we are going to find out mathematical response of filter. So, in this case just try to understand this, there is any circuit. So, for that circuit we are interested in finding out transfer function. Transfer function is nothing but the ratio of output upon input. So, here I am going to find out the ratio of output upon input. So, for example, this is input, this is output. So, what will be the output? Output across capacitor upon output across R plus output across C, like this. So, this is nothing but multiplied by input. So, VIS. So, V naught S upon VIS will be what? Output, that means impedance of this capacitor, that is 1 upon j omega c or 1 upon SC upon this R plus 1 upon SC. Take LC and then we can solve 1 upon SC R S C plus 1 upon SC. C and LC will be cancelled out. We will get 1 upon RCS plus 1. This. Divide both numerator and denominator by RC. We will get this. So, this is 1 upon RC, 1 upon RC. So, if you will solve it, you will get it like this. That means H omega is equal to 1 upon 1 plus R C omega square, or even you can solve it from here also. This is what 1 upon 1 plus S is what? J omega R C. Okay. And omega, this omega c is equal to 1 upon 2 pi R C. Okay. So, if you will put here, you will get it like this. 1 upon this. If you will take its magnitude, you will get 1 plus 1 upon 1 plus RCS or 1 upon 1 plus omega upon omega c square, like this, omega upon omega c square, which is nothing but 1 plus f upon fc square. This, finally you will get this after putting value of omega c. Okay. So, this is the analysis of patch filter. That means I have not taken anything related to operational amplifier till now. After taking this operational amplifier, the response up to this stage we have already find out. Now, we can multiply that with the gain of this, which is DC gain, which is 1 plus R2 upon R1. So, output voltage gain or total voltage gain will be equal to final output upon Vin. So, this is AF, the gain provided by operational amplifier, and 1 plus F upon FC is the transfer function of passive filter. So, if we will see here at very low frequencies, when f will be less than fc, f will be less than fc, this term will become very small, that means it will be nearly equal to 1, and this voltage gain will be nearly equal to AF. When f will be less than fc. At f is equal to fc, these two will become equal, that means it will become AF upon 1 plus 1, that means 2, and its under root. So, at f is equal to fc, V out upon V naught will be equal to AF upon under root 2, which is nothing but which is cutoff frequency, which we already seen that at cutoff frequency again becomes 1 by under root 2 times of maximum. This is what. And so, now at very high frequency, what will happen? At very high frequency, that means when f is much greater than fc, this term will become very large. When numerator is small and denominator is very large, that means this AV will become very small, like this, much less than AF. So, we can conclude that yes, at low frequency signal is passing, at cutoff frequency gain is AF upon under root 2 times, at f is much that when f is much larger than fc, this factor will be much less than AF. That means as frequency is increasing, gain is decreasing. This is what happens in case of low pass filter. So, this is how we can prove that yes, this is low pass filter, and how does it will behave? It is this. So, we need to remember this frequency response of low pass filter, where each and everything is mentioned. Yes, this is maximum gain minus 3 dB gain, it is related to cutoff frequency, this is minus 20 dB per decade slope, this is pass band, this is stop band. We need to remember these all things. So, this is the formula of R is equal to 1 upon 2 pi RC. So, if you have any question given to you to design low pass filter, we can simply use this relation, and we need to assume the value of capacitor. So, for example, you can assume the value of capacitor as 10 nanofarad, and depending on that you can find out the value of resistors. In this case, by taking capacitor value this, you have find out resistors value like this. And next thing is AF is equal to 1 plus R2 upon R1. If they are asking, in this case they are ask you to design the low pass filter having gain of 2 and cutoff frequency of 1 kilohertz, okay, and they have given capacitor value 10 nanofarad. So, I have taken 10 nanofarad, I have found out this resistor. So, that passive part is completed. Now, I am going to design the part associated with operational amplifier. So, in this case, I need to find out the value of R2 and R1, and AF is given as 2. So, it will be R2 upon R1 is equal to 1. So, you can take equal values of R2 and R1, and in this way you can design low pass filter for any desired frequency and for any desired gain. Thank you.